Fundamentally, a ledger is a database used to track the changing state of assets, whether those represent digital currencies, property deeds, or security certificates. In a traditional system, a central server processes every incoming input and updates the balance sheet. As shown here, transactions sit in a pending stack until a central processor executes them to create a new ledger state. That processor is the single source of truth. Every participant must rely on the administrator's integrity to keep records accurate. This raises a specific architectural challenge. What happens to the database if we remove that central administrator entirely? Without a central authority to verify inputs, the system is immediately vulnerable. Any user could attempt to forge transactions or edit the database records directly. Designing a decentralized system requires us to solve a massive engineering problem. We must find a way to verify information in an environment where no one is in charge. To begin, we must shift the architecture. We distribute the single database across a peer-to-peer network made up of thousands of independent nodes. In this decentralized model, we strip away traditional identities. As this visualization shows, names and personal accounts are replaced by unique alphanumeric cryptographic addresses. But because everyone holds a separate copy of the ledger, varying network speeds mean nodes receive conflicting data at different times. This creates a core paradox. We have to prevent malicious actors from altering balances or spending the same asset twice, but there is no central authority to stop them. A trustless state is achieved by stacking cryptographic proofs and applying algorithmic game theory. To build this engine, we must first solve the most basic requirement: proving identity and authorization without relying on a central ID provider. Our first engineering challenge is proving that a transaction was actually authorized by the owner of the asset in an anonymous network. We use public key cryptography to solve this. It separates a user's public identity, their address, from their private authorization, the key. We rely on cryptographic hashing. As shown in this SHA-256 diagram, input data is converted into a deterministic 256-bit string. Notice the disparate outputs on the right. Because of the avalanche effect, changing a single comma creates a completely different hash, making tampering instantly visible. To authorize a transfer, a sender creates a digital signature. This process involves combining the hash of the transaction with the sender's private key to produce a unique cryptographic proof. For verification, nodes use the sender's public key to decrypt the signature while calculating a fresh hash of the incoming data.
If the decrypted hash matches the calculated hash exactly, the network knows the transaction is authentic and unaltered. Cryptography provides a mathematical guarantee of who sent the data and what the data contains, removing the need for human trust. Individual verified transactions are not recorded one by one. Instead, they are batched together into data containers called blocks. This diagram illustrates the internal architecture. Every block contains transaction data, a timestamp, and its own unique hash identifier. The chain mechanic works by requiring block n to contain the specific hash of the preceding block n-1. Imagine a malicious attacker attempts to alter a historical transaction buried deep inside block n-1, hoping to covertly steal funds. Because of the avalanche effect, changing that data instantly changes the hash of block n-1. The broken link cascades. Block n now points to a hash that no longer exists, mathematically invalidating every subsequent block in the chain. This interlocking structure engineers historical immutability, making the ledger functionally tamper-proof. This leads to the final problem. What happens if two valid but conflicting blocks are proposed to the network at the same time? This creates a network fork. The decentralized nodes must determine which version of the ledger represents the single truth. This is the Byzantine general's problem: reaching a unified agreement in a system where some participants may be acting maliciously. An attacker could attempt a Sybil attack, where they spin up thousands of fake virtual nodes to outvote the rest of the network. Consensus mechanisms solve this by tying voting power to scarce economic resources, making forgery cost-prohibitive. The original, battle-tested consensus algorithm for this is proof of work. Proof of work requires nodes to expend physical computational hardware and electricity to earn the right to propose a new block. To alter a proof of work chain, an attacker would have to outcompute 51% of the global network, an economically ruinous task. Proof of stake provides a modern, energy-efficient alternative mechanism. Proof of stake replaces energy consumption with financial collateral. Validators must lock up cryptocurrency to participate in the voting process. If a validator acts maliciously, the network triggers a slashing mechanism, which algorithmically destroys their locked capital. Consensus mechanisms are the final layer of the engine, converting cryptographic rules into mathematically guaranteed economic security. Our build is complete. Cryptography ensures data integrity, chains provide immutability, and consensus creates a shared truth. There is an engineering trade-off, however. Achieving this level of global consensus makes these base layer blockchains inherently slow. To solve for scale, modern systems use a multi-tiered architecture from L0 to L3.
Layer 1, the base blockchain, handles high-security tasks like consensus. Layer 2 manages high-speed execution off-chain, mathematically rolling results back down to Layer 1 security. This complex architecture achieves several specific characteristics: total decentralization, historical immutability, and operational transparency. Blockchain is a foundational network protocol. While its first uses were financial, its broader purpose is to provide the infrastructure for routing and verifying state. Just as TCP/IP routes data across the internet, blockchain is engineered to route value and ownership. This technology provides a definitive solution to the problem of digital trust, replacing administrative oversight with the certainty of open mathematics.